A rubber band powered plane can be wound up to store energy that can then be used to power a propeller for flight. And whilst a well-built plane can achieve impressive flight times, it still takes time to wind up the rubber band. So I want to build a 21st century wind-up plane using modern building techniques and supercapacitors that can be wound up in a matter of seconds using a hand crank generator, resulting in flight times that far exceed their winding time. A big thank you to the HP ZBook Fury and Intel for sponsoring today's video. Now, storing energy as electricity inside of a supercapacitor is very different from a rubber band, but they do have some similarities in that a supercapacitor can be wound up using a hand crank generator to produce electricity. And I did this in a previous project where I built a large radio controlled plane that was powered by supercapacitors instead of a battery. But it took over 2 minutes to charge by hand and resulted in a flight time of slightly less than 2 minutes. So to increase this flight time to wind up ratio, let's make the plane smaller and more efficient. A common material for small rubber band powered planes is balsa wood, as it's very lightweight, but it's also very time consuming to work with, which for prototyping reasons I want to avoid. So I'm going to 3D print this plane. Now, 3D printed plastic is slightly stronger than balsa wood and more durable for when the plane eventually crashes, but it's also far heavier at about 6 times the density. But being able to print a plane in a matter of minutes is a win in my opinion, and with a good design I still think we can build it to be very lightweight. We just need a method of easily covering the wing surfaces. In the early days of 3D printing, it was always a struggle to stick the prints down to the build plate, and a common solution was to use masking tape, which gave the build plate a textured surface to stick to. Now what I'm thinking is, can we use this to stick the 3D print directly to some thin tissue paper to create the wing surfaces? And fortunately, due to modern 3D printers having magnetic build plates, I can use some magnets to secure the tissue paper in position. So let's see if this works. Oh, it missed the magnets, that's a good sign. Let's fill in the extra slot. And is it sticking to the paper? It's looking good. I can't see any edges peeling up, and the print seems to look good. This could actually work. Okay, so the print was successful, so let's remove the magnets and see how well this has actually stuck to the paper. Do you know what? I think that is actually stuck incredibly well. And now all I need to do is trim around the edges and we have a wing. That is so cool. I then trimmed the excess paper from the wing and printed a test fuselage that has some nose weight so we can do some glide tests, and printed a tail section using the same tissue paper technique. And the total weight of this glider is just 3.8 grams. But does it fly? Okay, here we go. Oh, that glides really well. It flies so smooth. Okay, now let's compare it to a paper plane. So paper plane first. Glides okay. 3D printed plane. With the small glider showing promising results, I started designing a much larger plane that can carry a supercapacitor and motor. So this new wing was printed in 3 sections, and I used a curved template and a heat gun to bend the 3D print into an airfoil shape. But after gluing the wing sections together, it was clear it was far too flimsy. So I printed a new wing in just 2 halves and designed a complex wing structure to hopefully maintain a better wing shape. For the fuselage, I originally wanted to go with a 3D printed structure like this, but after lots of prototyping, it was difficult to keep the weight low whilst also maintaining strength in both the pitch and the yaw directions. So I've decided to go with something far simpler and lighter, a carbon fibre rod. And the wing can attach to the carbon rod using friction fit slots, so the position of the wing can be adjusted later when trimming the plane. I then printed a tail section that seemed roughly the correct size, and attaches to the carbon rod in the same way. Then a nose weight in the form of a steel bolt can be attached to the front of the plane for a glide test. And initially it seemed to glide really well. The wings flexed upward to create dihedral for roll stability, and the plane flew nice and slow. But then this happened. I first thought it was a bad throw, but watching it back, it's clear the wings caught the air and folded, causing the plane to enter an uncontrolled nosedive. And even when I threw it correctly, the wing would occasionally flutter and dive for the ground. It seems we need a new wing, but fortunately I can use the HP ZBook Fury to see where this design needs some changes. This thing is basically a desktop workstation in laptop form, as it's got the Intel Core Ultra 9 processor and Nvidia RTX Pro graphics card that I need for running my design simulations. So let's use it to run stress analysis on the current wing design. This reveals the same forward warping issue that we experienced in the real-world tests, and using these simulations will help me make adjustments. And being able to design multiple wing structures and immediately run simulations is far more time efficient than physically building a new wing every time. So I've run simulations on lots of different designs, but the wing structure doesn't seem to help much. However, we can reduce the aerodynamic loads by making the wings smaller. So let's get this printed out. Now this is only half the work of these projects. The rest is in the video editing, which on the large 18-inch display, editing diagrams, labels and physics explanations becomes much easier thanks to the extra screen space, especially when keeping track of several months of footage that needs to be cut down into a single YouTube video. Fun fact, this whole project requires 260 gigabytes of footage, which is a lot of editing. Oh, and also I use this laptop to produce all the 3D animations myself for this video. To do this, I take the 3D CAD model of the plane and use it to create these more detailed 3D renders, which can be quite demanding, so having that graphical power means I can render each frame much quicker, so it's not an overnight process every time I need to create these animations. And because it's a proper workstation, it's upgradable so you can add more RAM or storage down the line, which is a big deal if you plan on using the machine long term. Engineering is difficult enough as it is, so why not make it easier and faster with the HP ZBook Fury? To see more of its features, I've put a link in the description down below, so go and check it out. So despite having less wing area, how does this new design fly? Okay, short wing glide test. I can't believe how well this thing flies with such a small wing. And we've definitely solved the wing flexing issues. So we've solved the wing flexing issue and it seems to glide well, but it doesn't really look like a high efficiency wing. It looks more like a parachute due to its short square shape. Now the squareness of a wing is due to its short wingspan and large chord, and the ratio between these dimensions is known as the aspect ratio. And this specific wing has a low aspect ratio, which is great for structural reasons and manoeuvrability. But as the high pressure air under the wing flows around the wing tips, it creates large vortices, which increases induced drag and reduces efficiency. But if we increase the aspect ratio by increasing the wing span, the pressure under the wing is spread out over the larger span, resulting in smaller wingtip vortices and hopefully reducing the induced drag. And we can increase the aspect ratio further by shortening the wing chord, which makes it look more like an actual wing. And I also believe that the shorter wing chord will experience less aerodynamic torsional loads, as the centre of pressure will act closer to the structural centre of the wing, hopefully reducing any twisting moments. So this new wing is printed in two halves on a single sheet of tissue paper, which gives it a similar surface area and weight to the previous wing, which after gluing together and bending the airfoil shape with the heat gun, it was time for some more testing. What's interesting with this new wing is that it seems to flex a lot in the vertical direction, which is actually a good thing because it gives the plane a natural dihedral angle, which acts as roll stability during flight. And it doesn't seem to be as susceptible to torsional loads like the first wing. What I've also noticed is that the glide slope seems to be slightly better than the shorter wing, which I assume is due to the reduction in induced drag. Now it's time to build the supercapacitor and motor unit to produce a thrust, and due to the size of this plane, we need a capacitor that's both lightweight, but also stores enough energy for a decent flight time. Now I've used supercapacitors in many of my previous projects, and as the capacitors get smaller, their energy densities also reduce, as the weight of the capacitor's packaging and wires have more of an effect. So I spent a while reading through some data sheets and found a brand of small capacitors that have relatively high energy density. And if I add an extra column to this table displaying the energy density, you can see how much it increases with the larger capacitors, where the 100 farad capacitor is roughly 6 times better than the 1 farad capacitor. Though weighing in at 20 grams, the 100 farad capacitor is far too heavy for this plane. So I then extracted all the values from this table to produce a graph of energy density against capacitance, and it revealed an interesting curve. The energy density increases rapidly for the small capacitors, and then starts to plateau after the 10 farad capacitor. So I decided to order the 10 farad capacitors as they're a good balance in terms of energy storage, and at just over 3 grams, should be perfect for this plane. I then bought some micro brushed motors, which are often used in small toy drones, and they usually run off of a single cell lithium battery, which ranges from about 3 to 4 volts. And they use these cheap, low quality propellers as efficiency isn't their main priority. But because the supercapacitors are rated to a maximum of just 2.7 volts, we should be able to run a slightly larger and better designed propeller, which should help improve efficiency. I then 3D printed a lightweight bracket that holds the capacitor and motor together and mounts to the front of the plane using the same friction fit technique as the wing. Then to charge up the plane, I can use my homemade 3D printed hand crank generator as I built in a previous video. The only issue is I have no method of checking when the plane is fully charged. There is a built-in voltmeter on this generator, but it only turns on after about 3 volts. And because the capacitors are rated to 2.7 volts, this could cause them to explode. So I found a small analog voltmeter that reads from 0 to 3 volts, which I can mount in a 3D printed case and attach the necessary wires to charge the plane. And this works perfectly as I can plug the generator into the capacitor to wind it up in just a few seconds, and then plug in the motor to convert the stored energy into thrust. And with a total weight of the plane at just 15.6 grams, the weight per wing area is less than a paper plane. So let's see if it will fly. It didn't quite climb as much as I'd hoped because the plane needs to climb quite a lot during the first portion of the flight to make use of all the energy in the capacitor. But let's wind it up and try it again. Yeah, it doesn't quite have enough thrust. Fortunately, I have a slightly larger motor which should produce sufficient thrust. And I also redesigned the wing mount to raise the wing higher, as this reduces the obstruction of airflow behind the propeller. And because the thrust line is now below the wing, it should naturally cause the plane to climb in the early portion of the flight. Then as the capacitor discharges, it will level out and slowly glide down, hopefully using all the stored energy in the capacitor to maximise the flight time. Right, so today is test day. It's about -2 degrees Celsius out here, but there's absolutely zero wind, which is perfect. Oh, that's nice, that's nice. Plug in the charge lead, and it's already at 0.5 volt, so there must have been some leftover charge. But if we crank it, it gets to 2.5 volts straight away. Nice and easy. Here we go. Oh wow, that's got loads of power. Oh, it's fluttering. Oh no. I'm getting dizzy, I'm getting dizzy. Wow, that climbed way more than I expected. That actually flies really well. Can we get one more circle? I can't believe how long that flew for. That was so cool. Right, so after that flight, we're at about 0.5 volt. Let's see how fast I can charge it. That was pretty quick. Take it for another test flight. So plugging it in.
That's a good flight. That's up nice and high. Wow, that's gone really high. Don't fly over the fence, please, because then you will land on wet grass. Here it comes, here it comes, here it comes. Oh, perfect.
After 2 very successful flights, I recharged the plane and went for another. But the plane struggled to climb. I thought maybe the tissue paper had absorbed some moisture in the damp, misty weather, and was probably increasing the weight of the plane. And a few flights later, the damp tissue paper wing had completely lost all its strength. So I swapped it out for a shorter wing that had been sat in a box full of other spare wings. But it also didn't want to fly.
Yeah, look at this. These are wings which I haven't actually flown, they were just spare ones. I know they were quite flexible to begin with, but that's just ridiculous, and they're all like that just from being out in this cold, misty air. So I think I need to keep these tissue paper planes either for calm summer nights or indoor flying.
So despite the tissue paper struggling with the moisture, the ability to 3D print directly onto the paper means I can build a whole new plane in under 20 minutes. And for a plane that flies for 45 seconds from just 4 seconds of winding, I'd say this proves that supercapacitors are a genuinely viable way to make a modern wind-up plane. Thank you very much for watching.